Okay, so now I'm going to talk about the finite element method, and there's two books that I suggest having a look at. There's the Finite Element Analysis of Electrical Machines, and then there's by Untitled Chapter 1, and then Numerical Methods in Electromagnetics by Chari, Chapter 6. So the second one is available through the library link. So let's consider now a more practical problem. So consider a 2D problem with a current source. So it can be described by this second order differential equation. So we've got the magnetic vector potential, and take the derivative, second derivative with respect to x, plus 1 over permittivity, second derivative of AZ with respect to y, and then minus J naught. So that would be some current value, and in some positions, and then permeability is equal to mu naught mu r. So this is equation 1. So we want to solve this problem over a certain spatial region in 2 dimensions. And remember that the advantage of using the magnetic vector potential is that we only need to solve one term in 2D, and then we can take the derivatives of AZ with respect to x and y, and that will give us the by and the bx. So in order to solve this, we use the same process that we talked about, but we're only going to solve it using the Galerkin method. So so this is our differential equation. So the first part is to substitute an approximate trial function in. So substitute an approximate trial function AZ hat for AZ. So if we do that, now I'm not going to put the z on here. I'm just going to leave out the subscript z because we'll have other subscripts and it'll just get complicated. So I'm just going to write a, and from now on, so you should keep in mind that is just the AZ component. So if we substitute in the residual, substitute in the a trial function given by a hat, then we're going to get out some residual. And so this is not going to be 0 because again, the trial function is not perfect. It's not the exact solution, but we want to drive that to 0. So residual greater than 0 since not exact solution. So now using the weighted residual approach, we're going to multiply the residual by a weighting function and then integrate it over the domain. So we'll so if we do that, we've got the residual, the weighting function, and then now we have it's 2 dimensions, so we have to do a surface integral over the problem domain. And so this This is equation 3. So the residual equation is equation 2. Okay, so this is what we want to make equal to 0. So we want this weighted residual integral, it's weighted because it's got a W, so residual because it's got a residual term in there. So weighted residual integral to be 0 over the whole domain, whole problem domain. Okay, so now we have to put the residual equation into equation 3, and if we do that, we're going to get out, I'll put the double integral to make it clear. I'm going to get out 1 over mu naught del squared a hat del x squared plus 1 over mu del squared a hat del y squared times the weighting function times dx dy, and then that's minus j naught w dx dy, like that, and that's we want that equal to 0, so that's 4. Okay, now now it'd be better if we didn't have the second derivatives here. So we're gonna because that will remove a lot of the trial function terms. So we're going to change this so that it's a single derivative here and one derivative on the w. And in order to do that, we can use the integration by parts. So the order of the problem can be reduced by using integration by parts. So we have the derivative of f and g is equal to f derivative times g plus f times g derivative. So we can rewrite that as fg prime is equal to fg derivative minus fg. So now, and then we integrate all three of these. So in our case, we can choose f to be w here, and the derivative g prime, for there's two terms, so we can take the first term and just look at that, and that g prime would be the derivative, second derivative az with respect to x squared. So then in differential terms, we have we can write out this this derivative here as with regard to our problem as w for the first part, w times del squared az, az, not putting the az in there, del squared a del x squared is equal to del over del x w del a hat del x minus del w del x del a hat del x. And that's equation 5. And then similarly the second term here, so that's the del squared del x squared, del squared a del x squared, and the second term del squared a del y squared we can write out as using the same approach. And by the way, this here is actually called Green's first identity, which is a little bit unfair, I think, because it's just that he gets his name on that one, because it's just integration by parts really written out. It's just the derivatives of two functions, but it's called Green's first identity. And so then we can also write out the second term, and so that's going to be w times del squared a del y squared is equal to del y w del a hat del x that's a y minus del w del y del a del y, like that, and that's 6. So now we can substitute 5 and 6 into 4, and that will allow these second derivative terms to become first derivative. So doing that, if I substitute that in, we get, so we're trying to get the final equation that we can solve we can use to solve any second order magnetics problem, actually, in 2D. So substitute 5, 6 into 4, so we get out minus 1 over mu del w del x del a hat del x plus del w del y del a hat del y, and this should be a double integral here. And then we have dx dy plus, so that's the second term in 5 and 6. So that's here. This is a1, and this is a2. Okay, so that's this here, a1, a2, and then we have now this term here, the first part of equation 5, b1, it has a partial derivative here, and so if we evaluate this over the surface, then the derivative, the integral term with respect to x goes away, and we only have an integral respect to y. So this, when we evaluate this, we get a line integral. So that's a boundary condition because it's a line integral. And the same with this, but instead the integral term with respect to y goes away. So we get a line integral. So this here I'll call b2, and so we get, and now gamma is denoting a line integral. So we have W mu times del. What is it if it, now because I took this is a little bit naughty here, but this is a simple example, but I took this 1 over the permeability outside of the integral. That would mean that then the value doesn't change inside of that inside of that area. Okay, so now that's actually going to be okay in our derivation, because we're going to look at this for each little problem region, one part by one at a time, each triangle, it turns out. So that's okay at the moment, but this could be inside too, to make it look more general. So we have B2 and B1, and so those two terms are going to turn out to be line integrals. So we're going to have del A hat del x dy. That's the first. That's B1. There's no del x, and then plus the second term w over mu del A del y dx, like that. So this is B2, and then we've got the current J naught dx dy, and that is all equal to 0. So that's equation 7. Okay, and so then things get interesting. So this is the main point that's where we're going to start to substitute in trial functions. So before we do that, we need to look at what the trial function should be. But it's worthwhile to take a moment to discuss this equation here. I don't know if you're familiar with COMSOL. That's one commercial FEA program. Most finite element programs, they don't allow you to delve into the differential equations like this, but COMSOL is one that you can actually write out the equations in this form to solve problems. So this is in this program it's called the weak form, because which is really a misnomer, because it's actually a powerful form. But it's powerful because if you look at it, what this one equation contains is it contains the problem information for the surface region, plus it includes the problem information for the boundary conditions, and so and then also the source. So you have here the source, you have here the boundary conditions for the problem, and then you have here the subdomain condition. So this actually contains the entire possible problem. If you had a magnet, there'd be a different source term. There'd be a del cross M here, but that just adds some complexity to the equations. But the same sort of thing applies. So this is really it's not really weak. It's really quite powerful. Okay, so let me put a few notes in here. Note: equation 7, often called the weak form of a partial differential equation. And the term weak denotes that integrals enforce differential equation on an average sense. So what that means is that it's satisfying, if we could find a solution, it would satisfy if you could find a solution A that satisfies this, it just has to satisfy it over the whole integral. It doesn't necessarily have to satisfy it at point-by-point place, but over the whole integral, over the whole domain, it would have to satisfy it, right? Because you could think of problems where the values would cancel out across the domain to make the integral 0. That's why it's called weak. But it really is pretty clever, because you have one equation that contains the problem, the domain, the boundary conditions, and the source. If you think about it, most differential forms, they're separate. You have boundary conditions and differential equations, they're all separate. But this allows you to write the entire problem in one equation, which is very important if you want to solve a complicated problem in computer. Now, another point which we're going to use, and I'm being a bit generalistic here, but often the derivatives del ax del y on the outer boundary set to 0, yeah, we'll leave it at that for now. We're going to assume that's the case for now. Okay, we'll talk about this more. So let's assume for now, because otherwise it's going to be more complicated. So let's just make the boundary conditions, these two, 0. Okay, and so if the normal, if the derivatives are normal to the boundary is 0, then that's called the natural boundary condition. I think I talked about that before briefly. And just to confuse you, but it's not me that made this up, the term that I was calling the weighting function, that's not universal. Often it's also referred to as test function. I think that's what COMSOL uses, the commercial FEA program, if you dig in their manual. Or another one that's very popular is a shape function. But I'll try to use weighting function, W for weighting function. Because the interesting thing is the finite element analysis method, my understanding is it grew out of civil engineering and mechanical before it migrated to electrical. So electrical was a bit later in the use. So some of the terminology is somewhat mechanical sounding. Okay, let me write out a little bit more, and then we'll go into some more equations. think I'll do it. So just keep that equation in your head so I can refer to it and you'll know exactly what it looks like. That's the thing that we have to solve. So we're going to now talk about the weighting function, aka shape function, test function. So now, normally we cannot solve the equation 7, the weak equation, using a single trial function. It's not, if you think about it, most problems are not going to have universal material and across the whole region. They're going to be non-homogeneous, nonlinear, and the geometry is going to be complicated. So since the field region is typically non-homogeneous and or nonlinear and or geometrically complex, a single trial function is not going to cut it. A single trial function can not usually be found. Okay, so what do we do? So we want to solve a more complicated problem. The way we can do it is by subdividing. So however, if we subdivide problem domain into smaller regions, a solution for each region can be found. Okay, so for example, so say that's the problem region there. There's no solution to that, analytic solution, say. So now what we could do is we could break that up into triangles. Something like this, maybe. Like this. So rather than having one problem region, we now have, what is that, 6? 6. And so then we could have a trial function for each, inside of each of those triangles, and then solve the whole problem for each triangle, and have different trial functions. So you know how we solved the coefficients just before, and we had 2 unknowns. So you could think we'd have a trial function with 2 unknowns in each of these triangles, and then we have to determine the solution. So you can see where this is going, probably. This would become rather difficult to do on the blackboard, but it's a piece of cake for a computer to solve lots of unknowns. So the way to do that is to break this problem down and put it into matrices and then evaluate them. So that the process to do that, I'm going to outline. So in order to do it, really, the only thing we have to figure out is how to represent the solution for one triangle, and then we can extend that. So if we take this triangle here, and then I can just redraw it. Try to. That triangle has three points. So AK, and so this is the x and y axis here. Okay, so then the magnetic vector potential would have some value at point K here. So that would be xk, yk, and then down here it's going to have some different value, aj, which is xj. I can see I'm going to run out of space. I'll put it over here. This point here is going to have aj, xj, yj, like that. And then at this point here, this would have some other value, ai, xi, yi. So the xi and yi is a particular spatial location, and that will give a particular magnetic potential value. Okay, so at those 3 points, there's some value. So let's assume we know what those 3 values are at those 3 points. Okay, and we want to then use that information to determine what the value is within the triangle, given that we know the values at those 3 points. Okay, so assume we know what AI, AJ, and AK values are at node points. Okay, so that's so then what we can do is we can write out a trial function in terms of AI, AJ, and AK, and those trial functions have to satisfy those points, those values are there. So let's start by assume potential, magnetic vector potential at node I may be expressed as AI, XI, YI is equal to A1 plus A2 XI plus A3 YI. Okay? Now this is step 1 of the 5 steps that we discussed. This is the trial function writing out. And then similarly, and these A1, A2, A3 are unknowns. A1, A2, A3 are unknowns. Okay, and then we have AJ, XJ, YJ, and let's say that this AJ could be written in terms of 3 terms, A1 plus A2 XJ plus A3 YJ call that equation I'll call that equation 8. No, I'll call this equation 8 here. We were at 7, weren't we? And then, and this.
A1's the same as the other A1s?
Yeah. Just wait a minute. And then AK is equal to X. This is a little bit like the movie. You have to see quite a bit, and then hopefully it will come together. So then AK could be written as A1 plus A2 xk plus A3 yk, and we'll call that equation 10. Okay. So that's the that's the three. These are the three boundary values. The three values at the 3 point. These are the values at the 3 points. Okay, and so that's so we're assuming that we know AI, AJ, and AK. Okay, just assume that, and then what we could say, maybe I should have said this to begin with, before this part, but so then we could say that the field throughout the triangle can be written as a hat. So this is our trial function inside the triangle, is equal to A1 plus A2x plus A3y. And that's equation 11. So that hopefully that makes more sense now. This is the trial function inside of the triangle. Okay, and then this trial function, therefore, at xi and yi would be given by 8, right? Because it has to satisfy the boundary condition, and then we also need it to satisfy the boundary condition at point j and at point k. And so this is our trial function that we're going to use. So just one last step, and then I'll stop. So if we look at these, if we look at 8, 9, 10, does look somewhat like we could put that into a matrix. So what we could write is that we have the three values at AI, the three values AI, AJ, and AK, and they are equal to a matrix which has the spatial positions in with xi, yi, 1, xj, yj, 1, xk, yk, and then that's multiplied by A1, A2, A3. Okay, so this 11 is our trial function, and this trial function has to satisfy the conditions, the boundary conditions 8, 9, and 10, because we're saying that we know what the values are at those 3 points. So we have 3 points that we know the values at, but we have the spatial positions x and y. The thing we don't know is what A1, A2, and A3 are, the three terms in the trial function. Okay, so in order to do that, in order to find A1, A2, A3, we need to take the inverse of this matrix, and that's where we'll start next time. Okay, thanks.